Hi there, my name is David Burer with Leviton Manufacturing, and today we're going to be talking about some design considerations for LumaCAN networks. Specifically, we're going to be talking about what the requirements are for the network as a whole, and we're going to be talking independently about the individual power and data networks. And one of the things that I will mention to you when we get into the content is that power and data are two separate things, and you must address both of them to ensure you have a successful network. So let's go ahead and jump right on into it. First, if you want lots of nitty-gritty details, some calculations, and all of that, check out this white paper on our website. It is an award-winning white paper. It got #1 in the category of technical white papers for Leviton, 10 pages of everything you needed to know to be successful. However, what we're going to talk about today is really just an introduction to what LumaCAN is, as well as some good rules of thumbs to keep you having a good, safe, robust network. So first, what is LumaCAN? It's a proprietary architectural control network that is unique to Leviton. Proprietary means Leviton's the only company that's using this. We invented it, we have it trademarked, we have patents on it. It's not something that just anybody can implement, although we would absolutely consider licensing it to somebody. LumaCAN, of course, is LumaCAN. It's the network we're talking about, but the CAN part of it is short for Control Area Network. And that is not a Leviton invention. That actually was an invention by Bosch, used in the automotive world when they wanted to have a digital communication bus that ran throughout a car and could be used to connect systems together in a car. In fact, if any of you have heard about the OBD2 port on your car, it's a port that you can plug in and do some basic diagnostics work and kind of see how your car's operating. Well, that really is just a CAN port. In fact, even the stereos in your car now connect up to the CAN-based network. So it's very robust, it's very reliable, and that's one of the reasons why we selected it for our lighting control network. Much like any network, it has specific power and data considerations that must be observed, and we're going to be working through those today. So first, let's look at the physical layer. So the LumaCAN network uses Category 6 wiring using RJ45 plug connectors on each end. Now, can you use Cat5? Nope, we don't recommend you use Cat5. I mean, technically it should work, but it doesn't carry power very well. So our recommendation, in fact, more specifically our requirement, is that you use Category 6 cabling with RJ45 connectors on your network. Second, let's look at what a LumaCAN segment is. So for every LumaCAN segment, you have a maximum run length of 1,600 feet. No, that doesn't mean 17 or 1,800. That is a maximum run length of 1,600 feet and a maximum of 110 devices. So that means that every 1,600 foot length, you can have up to 110 devices. And in every segment, you can have up to 110 devices, even if it's less than 1,600 feet. Now, what about end-to-end? So end-to-end on a LumaCAN network, so think multiple segments connected together with repeaters in this case, you can go up to a maximum run length of 10,000 feet and you go up to 250 devices. So in between ports on a repeater, it can be no longer than 1,600 feet and no more than 110 devices. In between end-to-end, so the entire LumaCAN network, no longer than 10,000 feet and 250 devices. So how are devices connected together? Well, they really follow a daisy chain style topology, and I'll show you a picture of what that looks like here in a minute. Termination at either end of the network is required, and we provide termination plugs that basically get installed in every unused LumaCAN RJ45 connector on your network, and on any network you should have two, one at each end. Max width of repeaters is 7 and the max depth is 3. So that means you could go 7 floors deep and 3 repeaters wide on every floor and use that entire network, again, all within the segment and the end-to-end requirements. What are some things that you don't do? Okay, now the consequences for these things are severe, so please pay attention to this. First, Do not use shielded RJ45 connectors or cables. Our product is not designed for them. It doesn't require them. It does not improve anything. In fact, just the opposite. It makes it so that your system will not work reliably, and in many cases, not at all. If we find shielded RJ45 connectors or cables on your job, it will void the product and system warranty. If our field tech sees them, which he will because he looks at the connectors on the job, he will immediately cancel the trip with fee, and no field service or commissioning will continue until they are removed and replaced. Second thing on the don't do list, do not use pass-through, or some people call them feed-through connectors. Those are the connectors where you push the wire all the way through them and then snip them off at the end to get a connector. We do not support them on our systems. If we find them, it will void the product and system warranty. We will also walk off the job site until they are replaced. We cannot guarantee a reliable system if you use pass-through connectors. Next, do not exceed the maximum current capacity of your cable. We're going to be talking about it today, but every LumaCAN cable has a maximum of 1500 milliamps or 1.5 amps. Do not exceed it. If you do, it will void the product and system warranty. It can result in premature product failure. You also can have a non-passive end of life of wire, the product, or other building systems. We do not like wires getting hot in the wall. We don't support it. We don't allow it. Don't do it. Next on the don't do list, do not under or over voltage your system. Our power supplies are all rated for 24 volts. Some of them supply just a little bit more at about 26 volts, and that's okay. Most of our products have a minimum rating of 12 volts. A few of them have a minimum rating of 18 volts. You will see that on the data sheet. So do not provide power supplies in excess of 24 volts nominal on your system, and make sure that every device in your network has suitable voltage in order to operate successfully. If you do over or under voltage your system, it will void the product and system warranty, and it could result in inconsistent product operation. Now, one of the things you will note, and I'll mention this in just a couple of slides, that as voltage goes down, current draw goes up. So by not planning correctly, you can accidentally over voltage your system or over current your system, because at 12 volts, the current requirements is twice that as what it is at 24 volts. So these are very big issues. Again, I'm going to show you some really quick ways to make sure you don't have problems. Now, what are some things you do or you should do? One, use Leviton provided patch cords everywhere you can. They are certified when they leave the factory. We know they work. We can provide a patch cord to you for less money than you can build one yourself, and it's a great way to connect product together. We can build you cables all the way from 6 inches all the way up through 1,600 feet, and in most of our systems, we provide sets of 20-foot cables with them. Note that if you received a kit of cables with your product or with your system, we can swap them out should you need other lengths, so reach out to your local Leviton agent and they will help you do that. Other things you should do: test each and every cable run with a cable tester that can provide certified test reports per run, and label all the cable runs. Those two things go hand in hand. When you do that testing, provide that test report to the Leviton field tech when you get there. You will get a pass-fail on every wire. Anything that fails, fix it before we get there. And you will, most testers will also give you a run length, so you can get a nice report of every run and how long it is. So it gives you a quick way to validate that you haven't gone beyond your allowed maximum run length. Okay, helps us a lot. Do this. Next, don't intermix data cable runs with AC wiring. It's an NEC violation and your system won't work well, so don't do it. Next, wire the entire project per the TIA 568B standard. It is the one we recommend. It's the one we prefer. If your project requires that you do it through the TIA 568A standard, that's fine. Just do the entire project that way and do not mix them up. So these are just some things that you can do that will help you have a better network. So let's look at some network topologies. I mentioned earlier that the LumaCAN network is a daisy chain network. Some people think a better term for this is bus, and I could argue either way. But in our case, we call it a daisy chain because it's a chain of devices that are all connected together. Every device has two RJ45s on it, one for the incoming and one for the outgoing wire, and it doesn't matter which one you connect to each jack, just connect one to both. And you connect them in a long run, so there's no T's, there's no splices, there's none of that. One continuous chain of devices. Now, I mentioned that there's two RJ45s on it. Any unused RJ45 jack should have the termination plug in it. Okay, so don't take them out until you know that you need it. The second topology we're going to look at is a star. Now that's how Ethernet networks are wired, where every device goes back to a switch and it's one device on one run. Now we allow a hybrid of those two, so a daisy chain and star, that we call a home run topology, and you can use that when you use repeaters. So here's just a quick example of a little system with a 6-port repeater, and we've got a couple of devices on each run. In practice, you get a lot more than two, but you can see where you have these multiple daisy chains of devices all coming back to a central point, or in this case called a repeater. Now that LumaCAN repeater is a special device that allows you to connect individual 6 runs together. Okay, and you can use that to really build this home run network. That's the only way that you can combine multiple LumaCAN runs together is with that repeater. Now remember that I mentioned the term segment and end-to-end. Each one of these individual runs is a segment. Okay, so that's where you have your daisy chain, and that's where you have your 1,600-foot limit. So each one of these segments could actually be 1,600 feet long. All right, now we're going to jump into a cool tool that I really want to show you that helps you resolve the power side of your network. Pretty much everything about repeaters and topologies and layouts and termination, that's all about the data side of the network. Let's go ahead and look at this tool called Alfred and what it does for you. So first, it's a tool that can be used to determine your maximum run length based on your network load. Now, earlier I mentioned that you can have voltage drop. Now, if you think about the higher the load on the network, the more voltage drop you're going to have, which increases with the current draw of the network, and you can't go beyond 1,500 milliamps. You also can't go beyond the capacity of your power supply. So there's a balancing act here that's kind of a 3-dimensional balancing act that the Alfred tool helps you resolve. And you absolutely can do these calculations on your own separately and work them out. This just chart takes a lot of the work out of it for you. So to help you determine your maximum run length based on your network load, next, the minimum power supply size, and then finally, whether you need 24 or 23 gauge cable. Those are the things Alfred helps you do. So let's walk through an example here. So the step-by-step. First, you're going to identify your network load. Okay, so that's really add up the current draw of all the devices on your network. That's your total network load. Next, you're going to find the row in your spreadsheet corresponding to the current draw. Then find the column corresponding to your run length. And finally, use the intersection of those 2 points to determine the minimum power supply you need to have a successful, reliable system. All right, let's work through all of those steps. So first, total network load. So I'm looking at a system today, and our example system we're going to use for this discussion is a room controller, a DRC07, 4 smart packs, 4 sensors, 2 switches, and a phase cut dimmer. Okay, now on this network, I have a supply, so my DRC07 also is a power supply to the network. My smart packs provide their own power, so they don't consume or provide power. The sensors and switches are all consumers, and the 4-channel phase cut dimmer also requires LumaCAN power. Now the 2-channel is self-powered, but the 4-channel requires a little bit of power from the network to make it work. So here's what I do. I go look at my chart, and you can get this data get this information off the data sheets, or look at the design guide, and it will kind of give you this exact chart. And you'll see it tells me the current draw of each device. You can see where most devices have a range. For example, the digital switch is 50 to 25 milliamps at 12 to 24 volts DC. That means at 12 volts, it's going to draw 50 milliamps. At 24 volts, it's going to draw 25 milliamps. So this is expressing that important relationship I shared with you earlier, where the lower the voltage, the greater the current draw, and vice versa. That means voltage drop increases current, and you end up in this spin cycle that just sometimes doesn't end well. So we look all of that up for our voltage calculations, and when you're determining the total, you always calculate it at your supply voltage. So in this case, we're using the 24 volt numbers. So the room controller doesn't use any power. The 4 smart packs don't use power. The 4 sensors use 35 milliamps each. The 2 switches use 25 milliamps each. And the 2 phase cut dimmers use 100 milliamps each. And when you do all that math, you find out that your total current draw on this network is 390 milliamps. Okay? Next, find the row in the spreadsheet corresponding to your total current draw. Well, let's carefully look at that and kind of blow that up. You see our source voltage and total device load is right there. So we're going to work down that column until we find the next highest column beyond 390 milliamps. So you work down that chart, and you can see that they're broken up into 50 milliamp blocks. So the next highest block is going to be that 400 milliamp. And that's going to identify the row that we want to look at. Now, I'll show you that your max run right here, 1,357 feet, that's the maximum run you can go to stay above that minimum 12 volt limit. So more on that later. Next thing we're going to do is we're going to find the column corresponding to our run length. Now, for purposes of this discussion, we're going to assume that our run length is 350 feet. So across the top, we find our actual run length. Now, blow that up a little bit. There's our actual run length. You can see that they're split into 100-foot increments there. So the next highest one above 350 is 400. Now, if I had a 300-foot run length, use the 300-foot column. Anything 301 or above, you're going to use that 400-foot column. Now, go find the intersection of 390 milliamps, which is the 400 milliamp row, and the 350, which is the 400-foot column. There's my row, there's my column, and there's the intersection right there. Now, what does that tell us? That tells us that our maximum run length is 1,357 feet, and at 400-foot run length, I need a 470 milliamp supply. Now, here's what I want to point out to you. Remember, our total network load was 390 milliamps? Well, practically speaking, in order to run that successfully, I need a 470 milliamp supply at 400 feet. So I need a bigger supply than I thought I needed. So 470 milliamps required. Now, what's my power supply? Well, my power supply is the DRC07-ED0. If you look at the data sheet for that product, excuse me, you'll notice that that power supply can only supply 300 milliamps. So what's the solution? Well, we have several different power supplies you can use to augment it. Ultimately, I have to get to 470 milliamps. So I would recommend that you use the DRC00-ED0, which is an additional 500 milliamp power supply, and that'll push you up way over the top of where you need to be. That'd give you a total of 800 milliamp supply, which is more than sufficient for your network. So anyways, that's just kind of a quick way to use this chart. Now, some other things that I just want to show you. Oh, there's a chart that shows you some of the power supplies we have available. So some other things that I just kind of want to show you is that most of the time for most of our rooms, we're living up here in this area here because for the most part, we're doing LumaCAN networks within the room, and your load is relatively low and your run lengths are relatively short. So when you're in that situation, you're rarely going to have a problem. But let's say that I happen to be in a situation where I have a bunch of phase cut dimmers. Okay, remember all those phase cut dimmers are 100 milliamps each. So it doesn't take very big system to find yourself into this current draw range of 800 to, maybe all the way up to 1400 milliamps. Let's just say that I had 1,000 milliamps load on my network. Look, my maximum run is really 517 feet. You see that in this column right here. But you'll also note that as the network gets longer and I look at an actual, so maybe only a 200-foot network, that's not very long, I actually need a 1,310 milliamp power supply. So that's a much larger power supply than you probably thought that you needed. In fact, the reality is that even though you could run 517 feet, you cross the 1,500 milliamp boundary before you ever get there. So practically speaking, you can't really go much beyond about 300 feet. Okay, so if you're doing basic calculations, sometimes you miss some of these finer details because you have to consider your total device load, your actual run length, and then your voltage drop and the power supply size that you need. So basically, take your device load, find the row, take your actual run length, find the column, and then make sure your power supplies are big enough. All right, a few other notes. Any cell with green fill, okay, so that's all of this section up here, or if you're looking at a version of this in our install sheet, they're going to be the shaded cells. You can use 24 gauge or larger LumaCAN cable. Now, all of the patch cords we provide you are 24 gauge cables. If, however, you don't have a green cell, so you're in one of the clear fill cells, you have to use 23 gauge or larger cable. Okay, that's just a requirement because the cable's not big enough to handle the current load. 24 gauge cable can only handle up to an amp, so anything up between 1 amp and 1500 milliamps needs the larger cable. Next, all cable must have a resistance of 14.5 ohms per 100 meters in order, or better, in order for these calculations to work. Now, most Cat 5, Cat 6 is at least that good. Some of them have a lower resistance, in which case your calculations actually get a little bit better. These were all done at 14.5 ohms per 100 meters, which is about the worst case that we commonly see. Any cell with a tilde or a dash in it, just not supported at all. So you just simply can't do it. But anyways, so there you have it. So what this does, gives you a way to wrestle those 3 dimensions, make sure you have big enough power supplies, make sure you don't exceed your maximum run length, and you're going to have a very safe and reliable system. So what do you do if your system's not, or if your system isn't supported? So you hit into some of those other categories. Well, if you hit those categories, you can either add a midstream power supply and segment your network. So like in the case of that example that we were at, add that DRC00-ED0 power supply, go put that in the middle or into the network, create 2 power supply segments, and you're off and running. The other thing you can do is change your topology a little bit, add a repeater out there, put it in the middle of the run, and make all of your runs shorter. So sometimes you can do that, and that'll actually improve the situation as well. So a lot that we kind of ran you through there, but basically just wanted to talk to you about some basic power and data considerations for LumaCAN networks, as well as to how to use the Alfred tool to make sure that you have enough power and make sure your power supplies are big enough on the network. As always, for additional information, please check out our website, leviton.com/GreenMaxDRC, which was a shortcut to a page that gives you everything you wanted to know about DRC networks. Also, check out the communities.leviton.com forums. Look under commercial lighting controls and then distributed network controls, and you'll find DRC under there. Thank you for spending some time with us today, and thanks for using Leviton.